As Jussi introduced, my professorship is micro and nanoelectronics. And that means that I work and do research on materials and devices with very small dimensions. Before going into the details, I would like to present something about the motivation and the driving force for my research here at Aalto. I've tried to somehow picture that here in this slide. So it's been very interesting to follow the huge development that we have all seen in microelectronics and how it's actually affecting our daily lives today. I remember when I started as a bachelor student in a university about 20 years ago, I bought my very first mobile phone. And I remember it was really, at that time it was not common to have a mobile phone. It was really bulky, really heavy, didn't have any memory at all, so I couldn't even use I had to memorize the numbers in my head because all I could do with it was to dial the numbers. But it was still awesome. It was mobile. I also remember it was really expensive. And same applied to the computers. So as a student, I couldn't afford a computer of my own. So thinking of that and what has happened now only a few years and what we can do with the tablets and how the prices have gone down, it's really amazing. And how this is possible is that the researchers have been able to develop further the microtechnologies and starting to use novel nanotechnologies, new materials, so that we can shrink the device dimensions to smaller and smaller. And when you do that, you get better performance, higher speed, and often also a lower price because you can pack things more densely and with the same substrate size you can actually sell more chips. So now I'm thinking about if something else similar could happen that could also impact our daily lives, maybe even more, and that's related to the big energy challenge that we are facing. And so far I've been really convinced when I've been following this energy discussion and more specifically the photovoltaics field, how it has developed and especially how big potential that has, that I'm sure there will be some sort of energy revolution in the near future, and I definitely want to be part of that too. And at the moment, since I have background in this microelectronics and I've seen the revolution in silicon technologies, the motivation is to now try to do the same thing for photovoltaics. So at the moment, we're actually quite in the beginning where we could be. So we're using the same material that enabled the revolution in microelectronics, so namely silicon. And we're using same fabrication technologies, but the efficiency of the solar cells is not yet as efficient as it could be. And as a result, we actually have to use rather large solar cells. So if you really want to produce a lot of energy, what you need to do is use a lot of area. So now as a researcher, my goal is that we make them more efficient. Same way as we did with the microelectronics, we can shrink the size and eventually we do not need to use such enormous areas, but much smaller devices are enough. And most importantly, with the device shrinkage, that there will be also the price that will be reduced considerably. That's even more important in the energy questions than maybe in the microelectronics. So, as an example, I have something how I started to do research on photovoltaic. This is the very first example. what I did and what we are still doing research on. So both now microelectronic devices and silicon solar cells use the same substrate material basically. This is sort of a cross-section of a wafer, and there we have the transistors, typically integrated circuits near the surface, and in microelectronics this other part of the silicon is basically not used, it's only a substrate. And some years back we have developed some techniques that we are using an insulator, which is often already there in many integrated circuits as a top layer. And if we introduce some charge, typically a positive charge in this case, we have noticed that there are certain impurities and defects in silicon which tend to in certain cases diffuse to the transistor areas and then kill the device performance there. But if we use this method where we can charge our insulators, actually those harmful defects won't end up to the devices because they are actually most of them positively charged. So very simple method, but it seems to work fine. And this is has been already used in industry, to my knowledge. So now, recently, we came up with the same idea that actually in solar cells we have an inverse problem. So unlike in transistors and microelectronics, where we are only using the device area near the front surface, in solar cells the current is flowing actually through the whole substrate. So in order to have a good solar cell performance, you do not want to have any harmful defects inside your bulk. So now instead of pushing them all these defects here in the bulk, we are using the opposite charge. So now charging the solar cell surfaces with negative charge, and we have noticed that we are able to actually collect these harmful impurities from the silicon bulk to the surface, and from the solar cell operation point of view, this is now ideal situation, and we can have actually current flowing. And this is what we have now. This was the idea, and we tested this in real devices, and the results are shown here. So we have the first, as a reference, standard state-of-the-art solar cells without any charge, or if we actually have a positive charge, like in case of microelectronics. And we expose these solar cells to sunlight. These defects now, which are inside the bulk of the silicon, react with light, and we see this typical so-called degradation phenomenon. This is well-known phenomenon that has been sort of the problem and is still somewhat the problem in even in the state-of-the-art solar cells. It's called light-induced degradation. So we have now demonstrated that if we use this idea that we got from the microelectronics, that now let's change the charge type to negative, we have been able to demonstrate that there is no degradation and no harmful effects going on under sunlight, and the cells are really stable. This will help us now to further understand the basic physics which is behind what is the actual mechanism, what kind of defects there are reacting with light, and develop maybe further techniques, because not always the charging is possible with all different kind of cell architectures. So sort of this will help us now to still study further some other aspects of this phenomenon, and hopefully come up with new ideas how to prevent this. So this is one active research area that we are currently still doing actively research on. So another thing, so in addition to the solar cell stability, we have been looking into the material price itself. Also, again, having the microelectronics background in mind. So in microelectronics, typically the starting material is needs to be really, really pure, because the devices are so small that even single atoms in a wrong place can cause really bad harm and device malfunctions. So in solar cells in the past, it was okay to have a little bit crappy material and a lot of impurities and stuff like that, and the efficiencies were still okay. But now when we really want to go to higher efficiencies and really try to reduce the size of the solar cells and get more power out of them, also these defects and the cleanliness requirements become very important. But from photovoltaics point of view, you cannot use the same starting material or same techniques exactly what you're using with the microelectronics, because it's too expensive. So we really need to live with the fact that we have a much dirtier material which is cheaper. So we have tried to find out some ways how we can still live with them without getting rid of them completely. So again, like Jussi mentioned in his introduction, that we do a lot of fundamental science too, to really understand the defect mechanism, what is happening in silicon, and when we do that, we can try to figure out solution when we really understand the physics behind it. And this is exactly what we have done recently. So we have taken such crappy material, which is very typical that in some ingots from which the crystals and cells are made, they typically contain a lot of, especially the edge areas, very low quality material. And what the industry is currently doing is that they actually cut just these away and don't use it, because you cannot make functional solar cells out of this crappy material. So now by manipulating them and tuning a little bit the solar cell process in a way that we try to put the impurities in a form that they are not anymore electrically active. They are still there, we cannot get rid of them, but we can make them into a chemical state where they no longer cause these problems. And as a result, we have shown that in a material we can actually transfer, this is exactly the same wafer before and after our treatment, to have also the edges of very high quality. And again, we have this demonstrated also in a device level. So we have fabricated solar cells with the standard process, starting with the same material, and if we do not do nothing, then the cell efficiency is really poor if it's made like this. But if we modify it by understanding what is going on in the cells, then we have been showing that actually we can have also from this really scrap material, which is typically thrown away, we can have as good cell efficiencies as from the expensive and clean material. Then third idea or thing that we have been developing is now, in addition to the stability and the material aspects, is the actual device. What can we do to actually make higher efficiencies? So a couple of main losses, again in the state-of-the-art devices, are related to the front surface. So there is two things. There is a reflection from the surface, because sunlight that is coming there, it sees an interface, and then as a result you get a pretty high sunlight reflection. And of course, as a solar cell, we want to absorb light as much as possible. So we want to avoid this reflection and absorb all the light into our solar cell, so that we can get as much current out as we can. Another loss is that typically the metal contacts are on the front side of the solar cell, so they cause both the shadowing losses and also reflect more light, because light cannot penetrate through these metal fingers or bus bars, how they usually are called. So a group of scientists earlier have shown that if actually this front surface is now not a planar and surface, but instead of consist of really small tiny nanostructures, where the dimensions are smaller than the wavelength of the light. What happens is that the light, because the dimensions are so small, they don't see any interface, and as a result they actually just smoothly don't see that the material has actually changed and just go, and basically there's no reflection, and with this surface you can absorb everything. However, this was shown more than 10 years ago that this kind of surface structuring is really beneficial. The problem is, and why it wasn't then studied maybe further, that quite soon it was noticed that while we have these nanostructures, even though we absorb all the light and we generate a huge amount of electrons, they also tend to attract the electrons. So what happens is that the electrons that are generated in our solar cells end up back to the surface, and then they sort of disappear there instead of traveling to this outside electric circuit, so that we basically lose them all. So as a result, the efficiency becomes poor even though you have a high absorption. So we have tackled that problem and found actually a good solution. And that is based on one of these famous nanotechnologies called atomic layer deposition. So we have excellent facilities at Aalto University for this technology. This is a really high magnification of one single peak here or somewhere here. And you might see a small few nanolayer thick layer on top of these tiny nanostructures, which we found out that they will actually generate a quite enormous electric field. So they are also charged. We can make a film which is highly charged, and then we generate an electric field which pushes away all the electrons. So now when we absorb all the electrons and we have this high electric field on the surface, we push away and can actually move all the electrons to this outer circuit, and now we can actually take advantage of this nanostructure without having the drawback that used to be in the past. And that was sort of the key or one of the breakthrough results that we had, and then we were happy to start to do solar cells on them with this idea. So as you see, and what has been demonstrated by also others, that the reflectance indeed is huge. There's a huge difference. This is like without these nanostructures you have pretty high 30% reflectance in most of the wavelengths of the sun. So this covers basically the sun spectrum, while with this nanostructures you basically have zero reflection. And now using this reflection result and the atomic layer depositing coating, we fabricated the solar cells, so the result can be seen here. This is so-called the quantum efficiency, which tells exactly the amount of electrons that we can actually collect to the contacts, which is then determining the efficiency. And we can see that in our solar cells we are really close to the 100% quantum efficiency, meaning that every single photon generates one electron, and then we can also have that electron in our external circuit. This was a result then published just a year before, which was the previous record for such kind of nanostructured solar cells. So they didn't have this idea how to prevent this disappearing of the electrons in the front surface. And as you can see, this quantum efficiency, especially in these blue wavelengths, which is close to the surface, starts to drop down, and we don't even see how low it goes. But this is sort of a quite nice result that we can improve the efficiency by 4% absolute with one single technology called innovation, so to say. And also one thing I would like to mention is that also we are always doing research mostly on rather relatively large solar cells, so the area on our record solar cells was much bigger than the previous record. And indeed, we have already proceeded to the panel stage, so we have made first test panels, and as you see, they really look black. And one option I actually forgot to mention you, what we are using here is that now we have also transferred all our contacts on the back side, so there is no further of these metallization shadowing losses either. They look, I think, more stylish than the current state-of-the-art panels. And then finally, the final benefit of this is that what I forgot to mention is that these nanostructures also help in one important aspect from photovoltaics is that when the sunlight is coming from different angles, it is also produces with this 22% efficiency electricity when it comes from low angles, while standard solar cells typically are optimized only for direct sunlight. So this is something that is, if you think about the energy production per year, they will produce more energy per year or per day or per hour because of this additional benefit they have. Then something quite recent, which I find very interesting myself. So now we have done quite a few years focused our research on photovoltaics, but again we got this idea that hey, there is another important field that is rising and needs attention, and we noticed that we could actually use this similar things that we have developed now for photovoltaics, we could use them for another application. So basically using a similar nanostructures than we used in our solar cells, and in addition to developing some things to avoid the actual p-n junction formation, which is the idea in current state of the art photo sensors, that there is a p-n junction that is generated, and this is how you make the image. So here we have developed a sort of a new concept that both uses the black silicon technology, so nanostructures, as well as these so-called inversion technology instead of conventional p-n junctions. And now we can, with this technology, we can extend our wavelengths from the sun spectrum also to, for instance, X-rays and deep infrared regions. And when we have published these results, it's been really amazing to almost still daily I'm receiving emails from different companies, different researchers who are working in completely different fields and applications that I didn't even know exist and could take advantage of this technology. So night vision or medical imaging, even space technologies have contacted us. Some companies doing mining technology, and they are using some UV sensors to detect the chemical composition of these minerals, and of course a lot of security applications using different imaging techniques. And the reason why they are so excited, I think, about this new idea is that we offer quite many benefits as compared to the state of the art or such devices that are commercially available at the moment. Here is, I have one example, what we did with one company recently. So we have an incoming X-ray here, and there is some material that is scattering the light, and then that's also one benefit what our technology brings now. Again, I mentioned from the solar cells that the sunlight can be captured from different angles, but also in this application, this low angle capture is very important, because nowadays they are using just like planar surfaces, and you basically lose all the scattered light. So they can only detect at the moment the perpendicular light. So this is another additional benefit. And as you see, this was the record response published last year by another group, and this is our photosensor at the moment, how much better photo response and quantum efficiency it offers as compared to others. And this is just a demonstration in a real X-ray imaging that we just also recently published, that with exactly same, we have the state-of-the-art photosensor and our Aalto's photosensor. We use the same X-ray gun and we make an image, and with our sensor we can get the output current is 49% higher, and this means that we can see with the image such things that we have never been seeing before. Or alternatively, this technology, we can reduce the X-ray power and the dose, and for instance, if you are imaging human beings, this X-ray dose is an issue, a health issue. So of course the doctors are looking for some technologies where you can reduce the doses, because then of course it's more safe to make the images. And this result means that they can reduce now so half of the power of the X-ray doses, which is already very, very significant, because even 10% would be high. So they can reduce now half of the X-ray gun power and still get the same image quality than with the state-of-the-art techniques. So that's why I think it's been kind of overwhelming. I didn't even realize myself that this has been such a interesting thing for many device field, and because of so many contacts that I'm now gathering and sort of orders for these photodiodes, we have also recently decided to have our own startup company who would start selling these, and I would still be doing, of course, research and looking for research collaboration, but yes, this has been, and I'm looking forward to the future story, how it goes. All right, that was all what I wanted to say. So concentrate on one topic and then apply that to different fields. So I think that will be my future thing to do. Thank you for your attention.